efficient with collision. And it has some nice principles for occlusion and so on as well. But in general, if you have an indoor environment, BSP should be used to box out the rough shape of the environment, and static meshes should be used for all the detail. Of course, meshes, or static meshes, the great thing about these is that the Unreal Engine kind of hands them off to the GPU, and the GPU totally handles rendering them, which makes them very fast to render per triangle. But because they can be complicated shapes, they can be really slow for collision, and that can be a problem for scalability and also for frame rates, because the client also computes collision. So we'll talk a bit about that too. The other great thing about static meshes is that they can be instanced, which means you can upload one static mesh to the GPU, and then you can use it in lots of different places. So, for example, in the environment you're looking right now, those microphone stands over here, there's 2 of them in this room, I guess. Those are instance static meshes. So the fact that there are 2 of them, in fact, the graphics engine saves on transferring meshes to the, across the bus to the graphics engine, because it only transfers it once, and then the graphics engine just renders it twice in 2 places. So you get some rendering performance saving there with instancing. And then finally, terrain is the third type. And terrain is optimized, well, you guessed it, for large open spaces, outdoor environments. It's a little bit less efficient per triangle than static meshes, but it's very efficient at collision. And because you're walking on terrain, collision is important, and you can't really save on that. So in general, if you've got a large outdoor space, it's better to use terrain for that outdoor area than it is static meshes because of the collision factor. A little bit of a trade-off there depending on detail, but in general, terrain for open space, static meshes for anything with detail, and BSP for the rough shape of your level. It's going to give you the best performance. Another thing to note is that in our testing, in general, static meshes with lots of polygons are not a problem. You can have, tens of thousands of polygons, hundreds of thousands of polygons even in static meshes, and generally the renderer will handle it very nicely. So don't worry about polys in your static meshes too much. There's lots of other places that tend to impact performance a lot more than that. So let's get to that. Textures. So textures consume a lot of GPU resources in different ways. So a little bit of background. Yeah, a little bit of background on textures. Scaling textures turns out to be quite expensive, takes a lot of work to do well. So what GPUs do today is they take pre-scale, they essentially have you scale your texture to several different sizes in advance. It's called MIP mapping. And that way they can, instead of having to take a humongous texture and scale it down to, a tiny little thing, they can take the next, the closest MIP map, which is the closest pre-scaled image, and just scale that. So they can start with a small image and just scale it a tiny bit, which is much more efficient. But of course, MIP mapping consumes extra texture memory. And texture memory is, not infinite. Graphics cards have a limited amount of texture memory. And if you exceed that limit, what happens is you have to transfer the textures back and forth from main memory. Essentially, the graphics card ends up having, essentially a cache of textures, and it's pretty efficient at rendering textures that are in the cache, but if it has to go back to main memory, you're virtually guaranteed to see a frame rate hitch. You'll notice that in very large environments, not just in the Unreal Engine, but in any kind of 3D graphics engine. When you move between areas and a whole bunch of new textures need to be swapped in, you'll see a little hiccup where you get for a second, maybe you'll get 1 frame per second, and then you'll be back up to full speed once the textures are swapped back into the video card. So keep in mind that. So anyway, to combat this memory scarcity, DXT compression was invented, and it's very important to use it. Otherwise, it doesn't take very many textures to blow out your video memory and cause frame rate hitches. All right, so let's get to the thing that's very often the limiting factor, at least in the environments we've been building. That's materials and shaders. Now, materials and shaders are critical for making environments look cool, right? They are the things that give you, all the, glowing or wet or shiny, reflective, whatever, all the neat effects that make an environment come to life. Are the things that let you, change the color of things, or, layer up shadows, or mask things. There's all kinds of things you can do with materials and shaders. But you have to keep in mind that each one of those has the effect of having to render several textures typically, or do an operation per pixel on that surface. So depending on how you implement your complex materials, you can very easily create a material that is 10 times more expensive to render than a flat texture. And so that's something that's really worth keeping in mind when you're doing your textures. Make sure doing your materials, make sure you test them out, especially on low-end machines, before you commit to using that particular effect. Very often the materials and shaders can be very expensive, especially on integrated graphics machines. And particularly those ones that are per pixel effects, ones that include specularity or reflections. All right, so another factor in rendering performance that's probably not well understood by most people is rendering sections. So when Unreal renders, basically every time you the thing you're trying to render. And so the way Unreal does this is it tries to issue as few instructions as possible, of course, to reduce this overhead. But the things that drive it to, that generate that overhead are, for example, switching static meshes. If you have two static meshes, it's 2 render steps to render those 2 meshes. Curiously enough, if you have 2 textures on a static mesh, you got to do a render step for each texture on that mesh. So, it tries to bundle up the triangles. It's quite efficient within the mesh. So if you have 2 textures on a static mesh, it's probably going to do it in 2 render steps. But it's worth noting that if you have 10 textures on a single static mesh, that could be as much as 10 times slower than rendering the static mesh with a single texture on it. So this is where that idea about combining textures into a single texture that you UV map onto the object comes into effect. If you take a single texture and you just UV map it so that the top left part of that texture is on the front face and the bottom left is on the back face of your mesh, you can greatly reduce the number of steps, and that will improve your rendering performance by reducing these overhead of having to issue additional GPU commands. It's also true that rendering lots and lots of individual meshes is expensive. So, if you had an environment with boxes in it, for example, it's much better to create a static mesh that's a pile of boxes than it is to create an individual box static mesh and build a pile out of that in the editor. You'll see that in any professional 3D game that you look around and they build rubble or debris or whatever. They don't have a single rock. They have a pile of rocks.
That's an interesting comment, because you mentioned earlier about instancing meshes.
Yes.
And it sort of contradicts what it says earlier. So this is where I've always got a bit confused.
Yeah, so let's
when's instancing a good time and when's instancing not a good time?
Yeah, very good point. So there are trade-offs, obviously. So there's a bit of overhead, obviously, as we're talking about here, in rendering a bunch of individual instances. But that's cheaper than rendering. It's cheaper to render a bunch of individual instances than it is to render, like, if you have 10, let's say you had 10 pillars, and you if you had a choice, you could either make 10 individual meshes that are different for each of the pillars, or you could instance one pillar 10 times, or you could make one static mesh that has all 10 pillars in it. So that's kind of a hierarchy, if you like. The worst is 10 different meshes for the 10 pillars in terms of performance. Next best is you instance a single one 10 times. That's obviously an improvement. And then the very best is a single static mesh that has all 10. Now, there's a little bit of